Hi everybody, we're going to work a type 2 projectile this time. Here's an image that shows you what I mean by type 2 projectile. This is how I teach it. You can kind of break projectiles down into three types. You've got type 1, which goes from an elevated surface down to the ground level. It's going to make half of a parabola. Then you've got type 2s, which are going to make a full parabola. They leave from whatever surface. This could be on top of a building or it could be the ground, but they go up in the air and they come back down exactly the same amount that they went up. So they hit at the same level that they took off. And then type 3 are kind of a combination of things. It's a type 2 parabola to begin with. It's something that goes up in the air and comes back down, but instead of landing at the same level that it took off from, it actually falls further down. It actually makes a drop below the level of the horizontal that it started out from. We're going to work a type 2 this time. We're going to do an object or something that goes up and comes back down just as much as it went up. So we have a quarterback who launches a ball, and now for this, I mean, we're gonna play a little bit with how the ball is traveling, because obviously a quarterback is not going to be laying down on the ground when they launch a football. So let's just assume, you can assume that, you know, it comes back down just as far as it was off the ground. So if the quarterback is holding it 4 feet off the ground when he lets go of it, then it's going to come back down 4 feet. We're just going to assume it comes back down to the same level that it took off from. So this football here is going to be thrown up in the air, and it's going to come back down over here. I can't draw straight lines today. It's Friday, and it's after school. I should just go home, but you want videos. So ball goes up, comes back down. Now, I'm going to label the other parts of this. It says that it's thrown at 12 meters per second. Well, if you throw a football, you don't throw it straight. You throw it kind of at an angle. So this ball is going to go up, and we're going to label it as having an angle of 35 degrees above the horizontal. So, and the speed, the 12 meters per second, is going to go right here on this hypotenuse of the triangle. Now, when we do a type 2 projectile, what we're going to have to know in our heads is that if I work for this angle over here, the same things can be true of the angle on the other side. In other words, it's going to come back down at 35 degrees. If it was going 12 meters per second on this hypotenuse, then it's going to come 12 meters per second on this one. If this is a distance of 5 meters for this part, for half of the parabola, then it's going to be 5 meters for the other half. What we find out for one triangle is equally the same for the other. And so that's going to help us with our problems. Now, this is all I know at this point. The next thing that I'm going to have to do is I'm going to have to label. I tell my classes make an XY chart, and it's going to be the same thing we need to do here. We need to make an XY chart that labels what we know. On the x-axis, we know that we can find v, delta x, and t. There is no acceleration along the x-axis, so we could put a in here, but it's always going to be 0. So I tell my students to just know that they can find vexed, v, x, and t. You can find vexed as well over on the y-axis, but you can find 2 v's, because this ball is going up in the air and it's coming back down, and gravity is affecting it. So it is going to have an initial velocity, and it is going to have a final velocity. When it reaches the peak up here at the top, it'll have a velocity of 0 when it's on the top of it. Now, you can look at that as the initial velocity, or you can look at that as the final velocity. My students and I have kind of come to an agreement that we're going to work these with an initial velocity of 0, so we're working it as it's falling. We don't know its final velocity, but we know that up here at the top we're going to start at 0 and come down. We also know a for this, which is 9.8 meters per second squared, because it's being accelerated by gravity. And I know that it has a t, but I don't know what the t is. My next step. This 12 can't go into either of these v places, because this 12 has a vertical component and it has a horizontal component. So how I'm going to have to figure those out is I'm going to have to work with some trig here. I've got this lovely triangle. This is the hypotenuse. So I can use sine and cosine to work out the other little pieces of this. And so we'll see how this fleshes out in terms of space. Let's come up here. if I do the cosine of 35 degrees, then that is adjacent over hypotenuse. That will help me figure out the x velocity right here. And I know that the hypotenuse is 12. That gives me an x velocity of 9.8 and a bunch of digits meters per second in my calculator. I tell my students to store that number in their calculator and keep track of it so that you could use it later. And over here I can put in 9.8 and some dots. I didn't leave myself enough room to write units. We're going to do sine of 35. That's going to tell me the y component of the velocity, and that's also going to go over 12. The y component of the velocity, according to our trig, is going to be 6.8 in a bunch of decimals in meters per second. So that means this is going to be its impact velocity. This is the velocity that it comes off of the ground with, and this is the velocity that it's going to hit the ground with vertically. So it's traveling 9.8 to the right at the same time that it's traveling 6.8 up or down in the end. So I'm going to put that in here as my vertical velocity. Alright, well now we're getting somewhere. We've got some things over here. The question wants to know how far downfield is the receiver. Well, I'll use a different color. That's asking for this right here. How far downfield is going to be the x distance that this ball went from start to finish. How high does the ball go is going to be this right here. That is my second question, is I need to find this delta x right there. So a couple of things I'm going to have to think about is formulas. This is a pretty simple formula over here. There's only one formula that I can use on the x side of things, and that is v is equal to delta x over t. That's a pretty simple formula, but the problem is on this side is I don't have an x and I don't have a t. Like I can't do this unless I have t. So somehow I got to be able to find t. Well, that's going to have to come off of the y side. I know whatever time it is on the y side is going to be the same time on the x side. Now, since this one has both halves of a parabola, we're going to have to solve for a t and then basically double it. So we need to start looking at equations that we could work over here to come up with a t. And the simplest equation to use would be this one, that a is equal to delta v over t. I have an a, which is 9.8 meters per second squared. We're just, like we've told my classes, we're going to work this from a positive standpoint. We're basically working it, you know, kind of backwards in some ways, but we're going to come up with the right answers, and we're just going to be okay with that. Don't hate me for it. My initial velocity goes last, because remember this means VF minus VI. We have 6.8 and all those other digits minus 0 over t. So what we're going to end up with is a t that is equal to, let's see, I don't actually have that one done, so I'll plug it into my calculator real fast. We're going to end up with a time of 0.693 and a bunch of digits. That is how much time it takes it to go halfway. That is the amount of time it takes it to go up, and then it takes it that much time to come down. So what I tell my classes is since this isn't an answer, if it asked me for how long the ball was in the air, then I would need to double this time. I can either go ahead and double it in order to answer the distance over here, or I can work it with half the time and just simply double the distance. Hopefully that makes sense. I'm just going to choose to work it with this and double it. So if I now know t, if this t right here is 0.693, then it's going to be 0.693 for half of it over here as well, and then all those other digits. So if you can see my calculator, I'm just going to keep all of that in my calculator. You can store it in. And I'm going to take this over here, and I'm going to plug this t in right there. I have the v on that side. It's 9.8. It just so happens to be the velocity. It's a coincidence. It won't always work that way. I did not choose the acceleration due to gravity. Okay, that was a whole bunch of digits in my calculator. That's going to be equal to delta x over a time of 0.693 and a bunch of digits. When we multiply those together, I'm going to end up with a horizontal distance of, let's see, apparently I wasn't as prepared as I thought I was. I don't have all this stuff worked out. That gives me a horizontal distance of 6.82 and a bunch of digits, 6.82 whatever meters. Now, that's how far it goes for halfway. Whoops, my picture's up here. That's how far it goes in half the distance. So in order to find this for the whole way to the receiver, I'm going to have to double it. So that gives me 13.64 and a bunch. We need some sig figs here. If we go back to our original numbers, the 35 degrees only has 2 sig figs, and that was a part of coming up with my speeds. So I'm going to round this to 14 meters. So there's the answer to A. The receiver is 14 meters downfield. Whew, that was a lot. How high does the ball go? This should hopefully be a little bit easier. I have everything over here on the y side except for the x, so it's pretty much open season. You just need to find an equation that has a delta x in it. I have some options right here. Since it's accelerating, I cannot use, and I totally wrote this wrong, look at me. I don't know if I had it up here earlier or not, that it's v is equal to delta x. If it was in my first video, forgive me. I can't use this equation right here because it's accelerating, and this only works for an object that is not accelerating. So I've got to come down to these formulas right here. I must pick out of one of these. Well, there's only one that has delta x. So winner. Oh no, lie. It's Friday again after school. Have 2 that have delta x. What am I saying? Have 2 that have delta x. So it could be the middle formula, or it could be the bottom formula. I personally would just prefer to work this one, the bottom one, instead of dealing with time in 2 places. I mean, honestly, it doesn't matter. You should be able to plug this into either one to get our x distance. If you plug it into this one, you're going to use the half of the time. Okay? I'm going to plug it into the bottom one. I'm going to plug it into this one right here. VF squared is equal to VI squared plus 2A delta x. And we may not be able to see all of this on my screen at the same time. I can do this and get most of our problem up here. If we plug it in, VF is this whole 6.8 thing squared. VI is 0 times 2 times 9.8 meters per second squared times delta x. And when we solve this in the calculator, we are going to get a delta x. I actually have this one done, aren't you proud? Of 2.417 and a bunch of digits meters. Come back to sig figs. This was derived from the sine of 35 times, I think it was 12.0, but the 35 was going to knock us down to 2 sig figs down here. So we get an answer of 2.4 meters high. So the ball went 2.4 meters up into the air. That's a lot for a couple of things, but that's basically how the problems go. You start out, you find the vertical and the horizontal components of a velocity if it's one that's given to you on an angle. Then from there, you will most likely need to find time to find anything else. That's just a pretty good guess to start with. You can find delta x's as you need. You follow what the problem's asking and what it asks for, and hopefully we end up with all of the answers that you are hoping for.